Hello there, welcome back to our channel. And there is one question I came across in the Spice Circuit Simulator. I wanted to simulate the current voltage characteristics of a diode. So let's do that and see what information we can extract from this little experiment, which is going to be happening right now. So on your screen, you see I have opened the circuit simulator, and then I am going to go to the library of the components, which is right here. I click here and I am presented here with the voltage source. If I have typed the voltage or just VOL, I get this voltage right here. I will click OK. It's a voltage source that can be DC, AC, sine, pulse, piecewise linear, exponential, or SFFM. So I will click OK. I haven't chosen this, and then I click place it on the schematic. Then I press escape from my keyboard to get rid of that. Then I need a ground terminal, which is I place again, I press escape, and now this is a voltage source. Then I click wire, and okay, let me choose all components first, then I'll make the connection. So again, I go to component library, click here and search for diode. So here it comes, and I just click OK, and I will just place it next to the voltage source. So look at, and then I press escape button again on the keyboard. Now look, this is the diode D1. The model name is diode D. If I right click here, I see there is this properties of the diodes where manufacturer name is not there, type is not there. Similarly, the specifications such as forward current and breakdown voltage not mentioned. So okay, no problem. And if I right click here, I need to mention the DC value of this. So assuming that it's a silicon diode, I don't know yet it is germanium diode or silicon diode, what it is cut-in voltage therefore is. So I will just assume, and that I want to know after I run the DC operating point analysis, something like that. Or maybe sweep this DC voltage source and check the current flowing through the diode. So let's do that. If I assume it is germanium diode or silicon diode, so obviously I will choose a voltage greater than the forward voltage drop of the either of the diode. I assume I have series resistance of the practical voltage source, but I don't mention here, assuming it's an ideal voltage source. I click OK, and then I am there to choose the wire to make the connections from the voltage source to the diode, and then here it goes, and then back from diode cathode terminal to the oh to let me just adjust this right here, and back to the negative terminal of the voltage source. So now having done that, you see I have created my simple circuit. It's time to simulate, but what analysis we want to do. So I will click edit simulation command, and so many analyses are there. So I will choose DC operating point and ask the circuit simulator to compute the DC operating point, treating the capacitances as open circuits and inductance as short circuits. So I don't have any of them right now in my current circuit. So look at the syntax is .op. I click OK and place it on the schematic. Then that's it. Now I am all set to run the simulation. I click simulation and click run, or just this button right here, run. Now you can see what I note here. That is the voltage at node 001 is 1 volt. So obviously this is that net or the node here. And the current through the diode is 617 ampere. That is not true. that is not true. What we need to do is maybe place a resistor in series with the circuit so that we can actually do that. Okay, but without doing that, we can do one thing. Let's say undo here and right click the voltage source and just say I have a 10 ohm series resistance of the voltage source, and that is sufficiently enough to create the resistance into the circuit. So let me just use the drag option to uh, just place it somewhere so that circuit can be clearly seen. And now back to the simulation, click here. And now you can see that the operating points are much better. Now I have applied the 1 volt across the diode. It has a series resistance of 10 ohm in the circuit, and then the current through the diode is about 26 milliampere, which seems reasonably okay. And the voltage across the diode, the net 001 is 0.73, which seems to be a forward voltage drop of the diode. So how about we just right click this net over here, and I can just use this option, place .op data label. And if I do that, the voltage at this node or at this net is 739.4 millivolt with respect to ground, which seems to be a forward voltage drop of the diode. And that's how you place the series resistance of it. Okay, and the current through the diode is 26 milliampere. We just saw that. What if I right click the diode and I choose to have this kind of diode model from the manufacturer? The part number is 1N914. So here are the specs. Maximum voltage across the diode can be 75 volt. Maximum current is about 200 milliamps the diode can withstand. That's the SPICE model syntax. Scale current is 2.52 nanoamps, which is your reverse saturation current through a PN junction. Then RS is 0.568 ohm, 0.5 ohm, right? That's the series resistance of a PN junction, or the forward resistance, I would say forward resistance. Then N equal to some parameter linked to the diode, 1.75. That's the CJO junction capacitance of PN junction. When you connect P-type semiconductor with the N-type semiconductor, you have the depletion region, and that gives rise to the capacitance of 4 picofarad here in this case. And the other parameters you can verify yourself. Now let's click that. Now I have this manufacturer part. Let's see if there are some changes in the operating points. Click simulation. Remember, this is the 739.4 millivolt, and we'll say okay. And now the drop seems to have changed. That is 0.745. The current seems to be little variant. That is 25 milliampere. Okay, so you can do it for other diodes also. Another forward voltage is changed now. Again, right click here, pick new diode. Let's say I do it for this diode. Click OK and click run simulation. Look at this. You have the similar voltage and the currents. I am choosing the silicon diodes, and there are a variety of diodes right here from Zener, Schottky diodes, Varactor diodes, and so on, the LED, and there are so many diodes right here. Do we see a germanium diode here? Schottky diodes are there. We maybe will have some tutorial with the Schottky diode, what it is and all that. So we don't see any germanium diode. Okay, so maybe just silicon. So how about this silicon diode with that? Okay, but average current is 4 ampere. Yeah, is sufficient. Okay, so we click OK and run the simulation again and look at the voltage drop has changed 642 and 35 milliampere is the current. So that's it. Okay. Now what I want to do, I want to simulate the IV characteristics. Remember, we have a Schottky diode model of the theoretical equations that we have for the diode, which says the current through the diode, which is this current that is going to flow when the diode is forward bias, is given as IS in bracket e to the power VD divided by eta VT minus 1. So this is our Schottky diode model. And this IS is the reverse saturation current, and the current that flows through the PN junction, the leakage current actually. And the VD is the forward voltage drop, this value. Eta is for silicon is equal to 1, I believe, and VT is your KT over Q. K is the Boltzmann constant, T is the temperature, Q is the electron charge, and the value of it is about 25 millivolt at room temperature. So that's the value of, so you see there is this exponential relationship between the current through the diode and the voltage across the diode. This VD is also represented as base to emitter junction when you do the analysis with BJT, because BJT also has a PN junction. If you want to get the expression for the VBE from this equation, you will see the VBE is related to the ID in the logarithmic way. So logarithmic way. So take the antilog of this equation, you get the exponential relationship. And when you take the VBE from this equation, you get the logarithmic equation. We'll write it sometimes later. So graphically, this equation can be plotted as something like this. You have ID, and you have this applied voltage V1, which is this one that I'm going to sweep from 0 to, let's say, volts, V volts, 5 volt or whatever. And it, as this point is going to be this forward voltage drop or cut-in voltage, okay, 0.7 approximately. And till that there is a little current, and after that you have like a kind of exponential curve that you can say that will flow through the diode. Okay, and then you take the slope of this curve, that is the change in current and the change in the voltage. So that gives you a conductance, forward conductance of the diode. Let's say GM, that is delta V of delta I divided by delta V. That's the forward conductance of PN junction. So it's time, let's simulate the characteristics and see how it responds. So what I'm going to do, I will just right click this, and I know there is this simulation button. I did simulation command, go to DC sweep. I will type the name of the voltage source I want to sweep, that is V1. Then I will choose the type of sweep, linear, start value, let's say 0, stop value, let's say 5 volt, increment is 0.01. So here is the SPICE syntax that gets ready when I input the parameters. Here's the SPICE syntax, and click OK. Place it somewhere on the schematic, and now you see I can run the analysis. Click run. Oh, let me just minimize those two windows because that's not relevant to this particular tutorial. And here we are. So let's see the input voltage. Oh, what have I plotted? That is the node voltage. Is it? No, I don't want to plot the voltage actually. Let me, because that's the linear sweep I'm doing it. Okay, let's first delete this trace. And what I want to plot is of course, the voltage across the diode is there. And look at this, when I take you to the schematic screen at the bottom, extreme bottom left, you see the simulator prompts me to click to plot voltage at node 001, and the probe is highlighted on the schematic. But if I scroll down, then go down on the diode, I am getting the arrow downwards, and extreme bottom left of your screen, there is a instruction left click to plot current through the ID1, right click to edit. So I will just click left click here, and that's the current I have. Now look at this relationship. It seems like a linear variations actually, but that's not true. It is a exponential curve actually. So you see it starts from 0 milliampere. If we zoom in over this portion, so again we see the zoom in over this portion, and again click on zooming over this portion. So you see there is little current flowing, even if the applied voltage is 360 millivolt, which is lesser than the forward cut-in voltage drop of the diode. But thereafter you have a rise in the current, and that's the exponential behavior. Okay, and let me just zoom to fit, or maybe like this, auto range and 600 millivolt. Let's say zoom to fit. So if we like take it up to 2.5, so now this is how you get the curve. What if I just use a normal diode without a manufacturer part? Okay, so let's try to do that. I right click here, I get the diode here, and I will just place it on the schematic, then press escape, and maybe I need to just cut this part. I don't want this part. So I will just now drag this diode back to this position and run the analysis and see how the graph shows up. Again, I plot the so here it's a big change, but you see this part, you still have the current after current is rising after about 720 millivolt. So, okay, so that's the forward, simulating the forward characteristics of a PN junction diode.